In the previous topic, we have studied the behavior of the voltage and the electrical current in certain electrical devices, like the ohmic and the non-ohmic devices. And we saw that the voltage and the electrical current, they are related to each other by Ohm's law as V equal to I times R, where R would be a positive proportionality constant that we label it as the resistance of an electrical component. However, when it comes to solving a much more complex electrical circuit, meaning an electrical circuit that consists of a bunch of resistors that are either in parallel or in series with each other, therefore Ohm's law alone is not going to be enough in order to determine all the voltages and all the electrical currents across each electrical element. But in that case, you have to be applying a set of rules. A set of rules in addition to Ohm's law in order to establish certain circuit equations. Or in other words, in order to establish certain mathematical equations that are specific for the electrical circuit that you are studying. Therefore, after establishing these mathematical equations, you would be able to solve for all the voltages and all the electrical currents within that electrical circuit or across each electrical element. But what are actually these set of rules? In 1845, a German physicist, Gustav Kirchhoff, he actually developed a set of two rules that deal with the conservation of charges within an electrical circuit, and another rule which deals with the conservation of energy within an electrical circuit. So Kirchhoff, he basically established two sets of rules, one which actually deals with the conservation of charges within an electrical circuit, and another rule which actually deals with the conservation of energy within an electrical circuit. And these two rules, they were later on named after him, and they are commonly known as Kirchhoff current law and Kirchhoff voltage law. So the conservation of charges rule is now known as Kirchhoff current law, or simply we refer to it as the junction rule. And then over here, the conservation of energy is now known as Kirchhoff voltage law, and we refer to it as the loop rule. So as we can see over here, the conservation of charges is basically related to the electrical current, and the conservation of energy is basically related to the voltage within an electrical circuit. And that first law, we can refer to it as junction rule, and that second law, we can refer to it as the loop rule. Starting with Kirchhoff current law. So what's actually Kirchhoff current law? So Kirchhoff current law, or simply KCL, it states that the total current arriving at any node or a junction point, and later on we are going to define what a node is or what a junction point is. So the total current arriving at any node in a circuit is equal to the sum of all the currents that are leaving that node. So for example, let's consider that you have the following electrical wire, which is going to branch out into three different wires. So we have the main current carrying wire, so that wire is carrying certain current I. However, that wire now is going to branch out into 1, 2, and 3 different wires. So that main current is branching out into 1, 2, and 3 different wires. And in that case, since that main wire is carrying a certain current I, once that current arrives at that point over here, it's going to be divided into 3 different electrical currents. It's going to be divided into I1 across the first branch, I2 across the second wire, and I3 across the third wire. Now over here we define something called a node or a junction point. So what's a node or a junction point? If we have a look over here, we can see that at that point over here we have an intersection of 2 or more than 2 electrical wires. So whenever you have a point at which you have an intersection of 2 or more than 2 electrical wires, therefore that point we can refer to it as a node or a junction point. So over here, that point, we can refer to it as a junction or simply as a node. So since we have an intersection of multiple electrical wires at that point, therefore we refer to it as a node. So when the current I reaches that node, it's going to be divided into several electrical currents. So the main current I is divided into I1 across the first wire, I2 across the second wire, and I3 across the third wire. In that case, KCL states that the total current which is arriving at any node in a circuit, so let's call that node A, over here we have node A. So that electrical current which is arriving at node A in a circuit is equal to what? It's equal to the sum of all the currents that are leaving that node, meaning that I is equal to I1 plus I2 plus I3. So in that case we can generalize that equation in order to write it as that the summation of all the currents that are entering into a node is actually equal to the sum of all the currents that are leaving a node. Therefore, we can write down that the summation of I entering plus minus the summation of I leaving is actually equal to 0. And therefore, we can generalize that equation furthermore to be the summation of all the current is equal to 0 within an electrical circuit. And that statement over here that the summation of all the currents is equal to 0 is basically a conservation of charges statement, meaning that the net electric charge within a circuit is always conserved. So we know that the electrical current is basically the flow of electrons. So an electrical current, it consists of negative charged particles. So whenever we are validating that the summation of all the currents in a circuit is equal to 0, or whenever you are validating that the summation of I entering in a node is equal to the summation of I leaving a node, therefore you are basically validating that statement over here, which is the conservation of charges statement, which is none other but that the net electric charge within an electrical circuit is always conserved. That would be the first rule, which is called KCL or Kirchhoff current law. Now moving on to the second law, which is Kirchhoff voltage law, or which we can simply refer to it as KVL, or also which we can refer to it as the loop rule. So previously, Kirchhoff current law, we can also refer to it as the junction rule instead, and Kirchhoff voltage law over here, we can refer to it as the loop rule. So the loop rule states that the algebraic sum of the changes in electrical potential, meaning of the changes in voltage, in every element that consists a closed loop, it must be 0. So the summation of all the voltages in a closed loop is equal to 0. For example, let's say you have the following loop, which consists of resistor R1, R2, and over here you have resistor R3, and they are all connected to that battery over here, which has a potential V. In that case, Kirchhoff voltage law states that the summation of all the voltages across every element that consists that closed loop, it must be 0, meaning that the voltage of the battery minus the voltage across R1 minus the voltage across R2 minus the voltage across R3 is equal to 0. Therefore, the summation of all the voltages is equal to 0, and therefore that equation over here is a conservation of energy statement. So that equation is a conservation of energy statement, meaning that the energy within a closed loop, it should be maintained or it should be conserved at all times. So the voltage which is being supplied by the battery is being entirely distributed across each electrical component that consists a closed loop. So we don't have any deficiency in energy, neither any excess in energy, but rather we have a conservation of energy within a closed loop, meaning that the summation of all the voltages is equal to 0. Now over here you might be wondering how we have actually chosen the signs for the voltages across R1, R2 and R3. We are going to tackle that topic in a bit. For that matter, we are going to consider now an example where we can be applying KCL, where we can be establishing equations for Kirchhoff current law and equations for Kirchhoff voltage law, and show you how we are going to be applying each law and how we are going to take, or how we are going to consider the signs for the voltages whenever we are applying the loop rule. Let's have a look at the following circuit, which consists of a bunch of resistors of 150 ohms that are connected to two batteries of 4 and 12 volts. As I have said before, we are going to be applying Kirchhoff current law and Kirchhoff voltage law to that circuit, meaning we are going to be validating the conservation of charges within a circuit and the conservation of energy within an electrical circuit. Starting with KCL, or simply the junction rule. Now, before we start applying the junction rule, we need first to identify a certain current direction, a certain direction for the current. So we are going first off to choose the conventional positive direction of the current, which is the one that flows out of the positive terminal and into the negative terminal. So over here we have the positive terminal of the battery and we have the negative terminal, and we are going to be choosing the conventional direction of the current, which is the one that flows out of the positive terminal. Now, an additional thing that we need to identify would be how many number of nodes or how many junction points do we have within that circuit. So over here we can identify that first intersection of wires, which is node A, and over here we can identify a second intersection or a second junction point, which we are going to refer to it as node B. So now, after identifying the direction of the current, now we are going to be actually distributing the entire currents across each electrical element. So over here, that main current I, once it reaches node A, it's going to be divided into two different currents. Current I1 across the 100 ohm resistor, and another current I2 across 50 ohm resistor. Then I1, it keeps going, and then it flows through the 50 ohm resistors, and then it keeps going until it reaches node B. So over here at node B, we have I2 coming into B, we have I1 coming into node B, joining together and giving out the main current I. So over here, through that 100 ohm resistor, we have that same main current flowing through it and entering into the negative terminal. So now, after identifying the current direction and after splitting the currents across each electrical element, also after identifying the number of nodes that we have, now we are going to be applying KCL, meaning we are going to be establishing equations for the junction rule. Since we have two nodes, therefore we are going to be establishing two equations. So starting with node A. At node A we have the main current I coming into A and splitting into I1 and I2. So I is equal to I1 plus I2. Then at node B over here, we have I2 coming in, we have I1 coming into B and giving out I. So I2 and I1, they are adding to each other in order to give the main current I. So as we can see, the equation of KCL at node A is similar to the equation of KCL at node B. So in that case, you would have only to pick one equation. Let's say we pick equation number 1, and then we can carry on with it. So we neglect the second equation since basically they are the same. Now regarding KVL, now after establishing KCL, we are going to be establishing equations for KVL, or simply the loop rule. Now when it comes to applying the loop rule or KVL, you need to indicate within each loop the direction that you are going to be moving around when applying the voltage rule. Meaning that, are you going to be moving in a clockwise manner within that loop or in an anti-clockwise manner? So for example, let's say you are moving in a clockwise manner, meaning that you are starting with the voltage at the battery, moving on to that resistor, moving on to the voltage across that resistor until you reach that final resistor over here. And in a similar manner over here, let's say now you are moving anti-clockwise, meaning that you are starting at the battery, then moving on to that resistor, then moving on to that 50 ohm resistor until you reach that final resistor of 50 ohm. So we are going to be assigning two arbitrary directions. So these directions for the loop, they are totally arbitrary directions, meaning that you can choose whatever direction that you want, whether a clockwise or an anti-clockwise one. So for the loop number 1, I'm going to be choosing a clockwise direction, and for loop number 2 as well, I'm going to be choosing a clockwise direction. Now after choosing the loop direction, now we need to assign polarities for the resistors. The resistors themselves, they don't have a polarity. Like they don't have a fixed positive terminal and a fixed negative terminal. But the polarity in that case, it's going to depend on the direction of the current, like from which side the electrical current is entering that resistor. So since the electrical current is entering that resistor from that left side, therefore that side would be labeled as the positive terminal, and the other side would be labeled as the negative terminal. In a similar manner over here, I2 is entering that resistor from that side, therefore that part would be the positive terminal, and the other side of the resistor would be the negative terminal. And in a similar manner over here we have positive and negative. Then I1 is entering the 100 ohm resistors from the left side, therefore the left side would be positive, the right side would be negative, and in a similar manner over here we have positive and negative. So like I said, the resistors do not have a fixed polarity. They don't have a fixed negative and positive terminal, but rather the polarity in that case is going to be dependent on the direction in which, or on the side from which, the electrical current is entering that resistor. So now, after defining the loop direction, whether it's anti-clockwise or clockwise, and after assigning polarities to each electrical component, and of course over here we have also to assign a direction for, or we have to assign polarity for that battery. Now we are going to be applying KVL. We are going to be establishing two equations for loop number 1 and loop number 2. Now before we proceed, over here you might be wondering, why didn't we choose the conventional current direction to be that of the second battery? Now, since we have two batteries over here, we have chosen one of them to be the main supplier of the conventional current. And in that case, the second battery is going to be treated as any other electrical element. And of course, you might be wondering that our choice in that case is going to be affecting our values, but it's not. It's not going to be affecting the values, but rather it might affect the signs of the electrical current, meaning that, let's say that electrical current I1 over here, which is flowing into that battery. If after calculations of KCL and KVL, we have proven that I1, it has a negative sign, meaning that in that case you have to flip the direction of I1, meaning that you have chosen the wrong direction of I1. So instead of I1 flowing into the positive terminal, I1 is going to be flipped and it's going to be coming out of the positive terminal. In a similar manner over here, let's say after determining a value for I, that value of I, it has an associated negative sign. Therefore, that implies that the direction that we have chosen for that main current over here, it was the wrong direction, but rather we have to flip it. So instead of having that main current coming out of the positive terminal, it's going to be entering into the positive terminal. So in brief, our choice for the conventional current, especially when you have two batteries in a circuit, is not going to affect our values, but it is only going to affect the signs in our values. So let's say, for example, instead of obtaining a positive value for the current, you are going to obtain a negative value, which is going to be an indication that you have chosen the wrong direction, and therefore you need to flip, you need to revert the initial direction that you have chosen for that current. And in case you have obtained a positive value for the current, therefore you have to stick to the direction that you initially chosen. So like I said before, our choice for the conventional current is not going to affect our values, but only the negative signs. So back to KVL. So since we have two loops over here, we're going to be establishing two equations for KVL. An equation for loop number 1 and an equation for loop number 2. Starting with loop 1. So like I said, over here we are moving clockwise, meaning we are starting at the battery, moving to 100 ohm, to 50 ohm, and then to that 100 ohm resistor. So over here for that battery, we are moving through that battery from a negative terminal toward the positive terminal. And we know that a negative terminal, it implies a low voltage point, and the positive terminal, it implies a high voltage point. So we are moving from a low voltage point to a high voltage point. So over here we have a voltage lift. So we indicate that with plus V1, and V1, it refers to the voltage of the battery. So that plus sign over here, it implies a voltage lift or a voltage rise, meaning we are moving from a low voltage point to a high voltage point. Now arriving at that resistor. Over here we are moving through that resistor from a high voltage point to a low voltage point. So over here now we have a voltage drop, and the voltage drop is going to be indicated by a negative sign. So over here we have minus V2, which is going to be the voltage across that resistor. So a negative sign over here would imply a voltage drop. Now moving on to that 50 ohm resistor, which we are crossing from a high voltage point to a low voltage point. Again, we have a voltage drop, which we are going to indicate with minus sign, minus V3. And finally arriving over here at that final resistor, also which we are crossing from a positive to a negative terminal, meaning from a high voltage point to a low voltage point. Therefore, it's also a negative sign. We have a voltage drop, so it's minus V4 equal to 0. And that equation we can write it as plus 4 volts minus V2 which is I times R which is 100 ohm, minus V3 which we can write it as I2 times 50 ohms, and minus V4 which we can write it as the current I times 100 ohm equal to 0. So what we are proving over here, we are proving that the summation of all these voltages is actually equal to 0. That would be for loop number 1. That would be the equation for loop number 1. Now the equation for loop number 2. So again, for loop number 2, we are moving clockwise. So we are starting at that resistor, moving on to 100, to the battery, and then to that final resistor. So starting at that first resistor, 50 ohm, which we are crossing now from negative to positive, meaning from a low voltage point to a high voltage point. Therefore, we have voltage lift, which we indicate with a positive sign. So it's plus I2 times 50 ohms. Now moving on to that 100 ohm resistor. Now we are crossing that 100 ohm resistor from positive to negative. So from a high voltage point to a low voltage point. So over here we have a voltage drop, which we indicate with a negative sign. So it's minus I1 times 100. Then we are crossing the battery from positive to negative, meaning from a high voltage point to a low voltage point. Therefore we have a voltage drop. So it's minus 12 volts. And finally over here, that resistor, we are crossing it from positive to negative, also from a high voltage point to a low voltage point, which we indicate with a negative sign, minus I1 times 50 equal to 0. Over here you have to keep one thing in mind, that you shouldn't confuse between the loop direction that you have chosen within each loop and between the direction of the current. So now in that case, we are not following the direction of the current. The direction of the current, we used it in order to assign polarities for each resistor, whereas we are following the loop direction in order to establish these equations for Kirchhoff voltage law. So you have to keep that thing in mind. So now we have established two equations for KVL. We have that first equation and we have that second equation. However, we have here two equations and three unknowns. We have the current I, the current I2, and the current I1. So we have basically three unknowns and two equations. And we need to reduce the number of unknowns to 2 in order to be able to solve these two equations. So over here we have established previously that I is equal to I1 plus I2. So by replacing I in that case by I1 plus I2, therefore you are reducing your set of problem to a problem that consists of two equations of two unknowns, which you can solve very easily. So after you replace the current I over here and over there by I1 plus I2, you would be able to solve by using the conventional method these two equations in order to find a value for I1, and then you find a value for I2. After finding a value for I1 and I2, therefore I would be I1 plus I2. And like I said before, in case you have obtained a negative sign for any electrical current, that would imply you have to change the initial direction that you have chosen for the current in that circuit. So you can solve these two equations at home and you can try them at home. They are very simple and very easy to follow. Like I said, you are going to replace the current I by I1 plus I2. Therefore, you have two equations of two unknowns, which you can solve in a very straightforward manner. Now let's move on to the Wheatstone Bridge. That circuit over here, which consists of 4 different resistors, it consists of the Wheatstone Bridge. So we have resistor R1, another resistor R2, a third resistor Rx, which is an unknown resistor, meaning a resistor that we don't know its value and we need to determine its value of resistance. And then we have a variable resistor R3, which is basically a potentiometer. And then at the middle over here we have a galvanometer. That galvanometer is basically a voltmeter that is going to be measuring the voltage difference between that branch and the other one. And over here we have a power source supplying that circuit with a voltage, with a potential difference. Now the Wheatstone Bridge is used in order to measure the value of an unknown resistor. So the target of that Wheatstone Bridge is basically to measure the value of that unknown resistor Rx. And the Wheatstone Bridge, it works by balancing out two parts of a bridge circuit. So what are these two parts of the bridge circuit? That part over here, which consists of the resistor R1 and the resistor R2, it consists the first part of that bridge circuit, and the other part, which consists of the variable resistor and of Rx, it consists the second part of that bridge circuit. So the Wheatstone bridge, it consists of balancing out these two parallel parts over here. But what do we actually mean when we say that we need to balance out two parts of a bridge circuit? We know that the electrical current in a circuit, it flows from a high potential point to a low potential point. So when we say that the Wheatstone bridge is balanced, it means that the potential at that point is actually equal to the potential at the opposite point. Therefore, the potential over here is equal to the potential over there, and in that case, the potential difference between them is going to be zero. Therefore, the galvanometer would be reading zero value for the potential difference. And in that case, these two parts of the bridge circuit, they are labeled as balanced. So in order to balance out these two parts, the potential at that point should be equal to the potential at the opposite point. Therefore, the potential difference between these two parallel parts would be equal to zero, and in that case we have balanced out these two parts of that bridge circuit. So like I said before, the target over here is to find a value for that unknown resistor Rx. In order to find a value for that resistor Rx, we need first to establish an equation for that resistor Rx. So we are going to be applying KCL and KVL to our circuit over here. So as we have seen before, in order to apply KCL and KVL, we need to consider first off a certain direction for the current. We need to be identifying the number of nodes that we have, and finally we need to be choosing certain loop direction. So starting with the direction of the current. So the current, in that case, we are going to choose the positive conventional direction of the current, which is the one flowing out of the positive terminal. And over here we are going to name these intersections as A, B, C, and D. So over here we can basically distinguish four different nodes. Node A, where we have an intersection of more than two connecting wires, an intersection or node B, an intersection C, and finally a node D. So that main current I, once it reaches node A, it's going to split into two different currents. A current I1, which is flowing through R1, and over here we have current I3 flowing through R3. Then I1, once it reaches B, it's also over here, I3 over here, once it reaches C, it's going to split, let's say, into IG, and over here it's going to split into IX. So now we have IG and I1 coming into B and giving out current I2. Now in a similar manner, you could have also chosen the fact that I1, once it reaches node B, it can also split into IG, which is going to flow in that way, and I2, which is going to flow downward through R2. So basically the direction of the current in that case is not going to matter, as we have seen previously, since what matters in that case would be the sign that you are going to obtain for that electrical current. So in case you obtain the positive sign, that would imply that you have chosen the right direction for the current, and if you have obtained the negative sign, therefore you need to flip the direction and choose the opposite one. So IG and I1 coming into B and giving out I2, and finally we have IX and I2 coming into node D and giving out the main current I. So now, after assigning the direction of the currents, now we need to be applying KCL, or Kirchhoff current law. We are going to apply Kirchhoff current law at node B and at node C. So as I have said before, our target is actually to establish an equation for our X. So first off, we need to establish certain equation for the electrical current. So, or two equations for the electrical currents, an equation at node B and another equation at node C. So at node B, we have I1 and IG coming into B. So I1 plus IG coming into B and giving out current I2. And then at node C, we have I3 coming into C and splitting into IG and IX. So I3 is equal to IG plus IX. Now, after establishing two equations for the electrical current, now what we need to do is we need to apply KVL in order to establish equations for the voltages. So To apply KVL, we need to consider two loops. We are going to consider that first loop and that second loop. But then again, we also need to consider certain direction for the loop. I'm going to go with the easiest choice, which is the clockwise direction for these two loops. But before we start applying KVL, we need also to assign polarities for the resistors. So as we have seen before, the resistors, they do not have a fixed polarity, but rather their polarity is going to be dependent on the direction of the current, or on which side the current is flowing through that resistor. So over here I3 or I1 is entering into R1 from that side, from the upper side. Therefore the upper side is going to be the positive terminal and the lower side will be the negative terminal. In a similar manner over here I2 is entering into R2 from that side, therefore that will be positive, that will be negative. IG is entering into that galvanometer from that side, also in a similar manner, that will be positive, that will be negative. I3 over here entering from the upper side into R3, into that potentiometer, so R3 is basically a potentiometer, which is basically a variable resistor, so that would be positive, that would be negative. And then finally over here we have IX entering RX from the upper side, that would be positive, and that would be negative. So now after assigning the polarities, what we need to do next is we need to apply KVL. So starting with the first loop, loop number 1. So in loop number 1 we are starting at R1, going into R3, and finally going into that galvanometer. So we are crossing R1 from a negative point to a positive point, meaning from a low potential point to a high potential point. So over here we have a voltage lift, and the voltage lift is indicated by a positive sign. So over here we have plus I1 times R1. Then we are crossing that potentiometer from positive to negative, from a high voltage point to a low voltage point. Therefore over here we have a voltage drop, which we are going to indicate it with a negative sign, so minus I3 times R3. And finally the galvanometer, we are moving through it from positive to negative, so we have a voltage drop, so it's minus Ig times Rg equal to 0. So of course the galvanometer is going to have its own internal resistance R. Now moving on to loop number 2. Now in loop number 2 we are crossing R2 from negative to positive, from low to high voltage point. Therefore we have a voltage lift, so it's plus I2 times R2. The galvanometer, we are also crossing it from negative to positive, so also over here we have a voltage lift, so it's plus Ig times Rg. And finally Rx being crossed from positive to negative, so it's a voltage drop, so minus Ix times Rx equal to 0. So we have established over here two equations for KVL and over here two equations for KCL. Now before we proceed and solve for Rx, we have mentioned before a certain condition for which we are going to be determining Rx. Rx, like we said before, is going to be determined, or is going to be easily determined for when the two parts of the bridge circuit are balanced. So Rx is going to be determined for that condition when the two parts of the bridge circuit are balanced. Meaning that what? Meaning that the potential at point C is going to be equal to the potential at point B. So basically, in that circuit over here, after you connect your circuit on the circuit board, what you are basically doing is you are varying with the value of that potentiometer, of that variable resistor. So you keep varying with that value of that potentiometer until you get on the galvanometer a certain reading for the voltage of 0 volts. In that case, once you obtain 0 volts on the galvanometer, that would imply that the potential at that node is equal to the potential at node B. Therefore, these two bridges, they are balanced. They are balanced out, and the potential difference between them is actually equal to 0. So the key point over here is to keep varying that potentiometer, to keep varying the resistance of that potentiometer until the voltage, until the galvanometer is reading a potential difference of 0 between these two bridges. So Rx is determined when the two parts of the bridge circuit are balanced, meaning that when the potential at point C is equal to the potential at point B. In that case, we know that the current, it flows from a high potential point to a low potential point. So when you have 2 points at the same potential, therefore you don't have any electrical current flowing between them. The potential difference is 0, and therefore Ig would be equal to 0. So when these two bridges are balanced, not only Vc is equal to Vb, but also Ig is equal to 0. So the current which is flowing through that galvanometer is also equal to 0, because the current, it always flows from a high potential point to a low potential point, and over here we don't have that condition anymore, but rather we have two balanced bridges, therefore we don't have any current flowing between them. So in that case, Ig would be equal to 0. And we need to apply these two conditions in our case over here. So when the bridges are balanced, that would imply that the potential that is being read by that galvanometer is equal to 0, but moreover, Ig is also equal to 0. So over here we can cancel out that term. We can cancel out also that term Ig times Rg. And over here we can also cancel out Ig, and we can cancel out Ig from that second equation. Therefore we are left with I1 equal to I2, and over here we have I3 equal to Ix. So now we can simplify our equations. So going back to these two equations of of loop 1 and loop 2. So we have I1 R1 equal to I3 R3, and for loop number 2 we have I2 R2 equal to Ix Rx. Now what we are going to do is, over here we have equation number 1 and equation number 2. We are going to divide equation number 2 by equation number 1 in order to find an expression for Rx. Therefore, Ix Rx divided by I3 R3 is equal to I2 times R2 divided by I1 times R1. Now over here we know that I1 is equal to I2. So I1 and I2, they are equal, therefore we can simplify them. And over here we have I3 is equal to Ix. So I3 and Ix, they also cancel out, and therefore we are left with Rx over R3 equal to R2 over R1, from which we can deduce that the expression for Rx is R2 times the resistance R3 divided by R1. And that would be the final expression for Rx, which is going to enable us to determine a certain theoretical value for that unknown resistance Rx. Now for the Wheatstone Bridge part, we are only going to be applying it conceptually and not experimentally, since the experimental part, somehow it's a bit faulty and it's not yielding any good results. So we are going to be applying that part only theoretically. So like I said before, the key point over here is actually to vary with that potentiometer, with that variable resistor. So once you keep varying with that variable resistor, in that case you are varying with the potential difference between B and C. So you keep varying with R3 until the galvanometer is basically reading a potential difference between these 2 points of 0 volts. In that case, the potential at point C would be equal to the potential at point B. Therefore, these two bridges are balanced and you don't have any current flowing through them. Once these two bridges are balanced, you can get a reading for Rx. And over here, I'm talking purely experimentally. So experimentally, after you reach a point where the voltage on the galvanometer is equal to 0, therefore you can bring an ammeter and you can measure actually the resistance across Rx, which is going to correspond to the value of that unknown resistance that you need to determine. But the key point over here is to keep varying with R3 until Vg would be equal to 0. Now in our experiment, we are going to be applying that equation over here in order to determine a value for that unknown resistance. But moreover, they are also going to ask you later on to determine a certain value, a certain error on Rx, which is going to be none other but propagation of error. Since Rx is going to be dependent on R3, which is a variable resistance, meaning a resistance which we are varying ourselves, therefore it's going to have a certain margin of error on it. Therefore Rx is going to be dependent on one variable. So Rx is a function of one variable, therefore the error on it is going to be the propagation of error method. Now regarding R2 and R1, R2 and R1 they are going to be given. The values for R2 and R1 they are going to be initially given and not measured. Therefore, we are not going to consider any error on them. Therefore, our X will be dependent on only one variable, which is going to be that potentiometer or that variable resistor R3. So since the Wheatstone Bridge is not going to be applicable in our case, we are going to be building through simulations our very own Wheatstone Bridge in order to test it. So we are going to start by connecting a battery to a connecting wire. So a connecting wire goes into the positive terminal and another one it goes into the negative terminal of the battery. And then we stretch them out. Then we are going to bring another connecting wire and we are going to join it to the one above. Therefore, we are forming a node or a junction and another connecting wire connected to that junction above. And then we bring two resistors. One resistor, which would go over here, and another resistor, which is going to go on the other side of that bridge into the other connecting wire. And then we bring an additional two connecting wires, one on each side. And finally, we are going to bring two resistors in order to complete our circuit. So one resistor on the first side of the bridge and another resistor on the other side of the bridge. And finally, we are going to bring the remaining connecting wires in order to form a closed loop. And finally, we connect that circuit to the battery in order to close that entire loop. So as we can see now, we have a current flowing into that loop. So over here we have a connection of four resistors. So let's name that one R1. Let's name that resistor R1. That resistor would be R2. Over here we have the unknown resistor Rx, and over here we have the fourth resistor, which is the variable one, or the potentiometer, which is R3. Now, in that case, we are choosing over here the direction of the current, which is the flow of electrons. So we can switch it if we want to the conventional direction, or to the direction of the current that flows out of the positive terminal and into the negative one. It's not going to matter in that case which direction you are going to choose for the electrical current, since both directions, they are actually widely used. So, like scientifically speaking, the direction of the electrons is going to be the correct one. But the positive conventional direction of the electrical current is also widely used and accepted. Now, our target over here would be what? Our target would be actually to determine the value of that unknown resistor Rx. Now, initially, each resistor, it has a certain fixed value of 10 ohms. So over here, if we click on R1, it has a certain value of 10 ohms. Also R2, a value of 10 ohms. R3 and R4, they are all given values, fixed values of 10 ohms. Now what we need to do is, we need to switch the value of R1. Let's say we are going to choose certain value of R1 to be equal to 30 ohms. We are going to assign a certain value for R2 to be, let's say, 50 ohms. Now when it comes to Rx, which is the unknown resistance, we are going to choose an arbitrary value for it. So let's say whatever value that falls in the middle, whatever it is. And then over here we are going to click on R3, which is going to be our variable potentiometer, or our variable resistance. The resistance which we are going to vary its value in order to render these two bridges balanced. And like we have said before, these two bridges are balanced when the voltage at that point is equal to the voltage at the opposite point. Therefore, the potential difference between them would be equal to 0, and there is no current flowing between them. So for that matter, we are going to bring that voltmeter and we are going to connect it between these two bridges. So we are reading a negative value, meaning that we need to switch the plugs. Alright, so initially we are reading a value of 2.10 volts for the potential difference between these two bridges, meaning that initially these two bridges are not balanced and we need to bring them to a balanced state, to a state where the potential over here is equal to the potential at the opposite point. So for that matter, we are going to click on R3 and we are going to start by varying its resistance until the potential difference that we are reading between these two bridges is down to 0. So if we keep looking at that voltmeter, we can see that the voltage difference is varying. So we are approaching 0. Alright, so we didn't get quite exactly to 0, but rather we got to negative 0.01. That implies that we need to change the resistance of either of R1 or R2. So let's say we are going to be using 31 ohms for R1. So now we got exactly to 0. So after changing the resistance of R1 and after varying with the resistance of R3, therefore over here we have reached a certain potential difference between these two bridges, which is equal to 0, meaning that there is no current flowing between these 2 points over here, and therefore our bridge is balanced. Now what we are left to do is we are left to determine a value for Rx. So by clicking on Rx, we can see that its resistance is equal to 60.5 ohms. So in that case, after you acquire values for R3, R2 and R1, you can apply the equation that we have established previously, Rx equal to R2 times R3 over R1, in order to theoretically find the value for Rx and then compare it to the experimental value that you are going to obtain over here, which is 60.5 ohms. So initially during an experiment, that resistor Rx is going to be wrapped up. It's going to be covered with a tape in order to hide its resistance from you. Then by connecting that resistor in a circuit and by using over here certain combinations for R1, R2 and for R3, you are going later on to be establishing a certain value for Rx by using the theoretical method Rx equal R2 times R3 over R1. But in that case, there's going to be multiple possibilities for the values of R1, R2, and R3. Therefore, whenever you vary the value of R1, logically the value of R3, which is the variable resistor, is going to vary as well. And also, whenever you vary the value of R2, the value of R3 is going to vary as well. So in order to render that bridge balanced, we can actually find several values for R1, R2, and R3, which they are going to lead a certain value of 60.5 ohms for that unknown resistor.